So let's go ahead and talk about the ideal gas law and how this compares to the combined gas law that we just learned. So if you look here, this is the combined gas law, and we use the combined gas law when there's a change in condition. For example, if the pressure changes, we can calculate the new volume or the new temperature. If the volume changes, we can calculate the new pressure. And so we use this when there's a change in the condition. But what if no change is happening? Well, we can actually still figure out pressure, volume, moles, and temperature using the ideal gas law. And the ideal gas law is this equation right here, which is PV equals nRT. PV equals nRT. P is pressure, V is volume, N is moles, and T is temperature, just like in the combined gas law. Now there is one new letter in there, is R. I would call it a variable, but it's not a variable, it's a constant. R is the gas constant. Now a constant is different than a variable because a variable can change. A constant doesn't change, and so R being a constant will never change. It will always be this particular value right here. R is always 0.0821, and so we will always have R. Now what's nice about PV equals nRT is the way it works is if you are given 3 of the 4 variables, and again there's 4 variables, there's P, V, N, and T. If you're given 3 of them, you can calculate the 4th one. So if you're given pressure, volume, and moles, you can calculate temperature. And if you're given pressure, moles, and temperature, you can calculate volume, and so on. And so if you're given 3 of the 4 variables, you can calculate the 4th one. Now something that we need to keep in mind is that temperature has to be in Kelvin, pressure has to be in atmospheres, and volume has to be in liters. So when we're using PV equals nRT, our units need to be in those particular units. That is different than the combined gas law. In the combined gas law, temperature still needed to be Kelvin, but pressure could have been kilopascal or millimeter mercury, and volume could have been milliliters. So let's go ahead and do a practice problem. So let's take a look here. It's a pressure of 1.5 atmospheres, a volume of 2.0 liters, and a temperature of 48 degrees Celsius. That's degrees Celsius, so we have to add 273 to make it Kelvin. And the question is, how many moles? So that's what it's asking for. So the given, so pressure is 1.5 atmospheres. The volume is 2.0 liters. And the temperature is 321. Now, the unknown is what it's asking for, so use unknown, and the unknown is moles. So moles is what we are looking for. And in this situation, notice how we are given 3 of the 4 variables, and it's asking for the 4th. Notice how there is not a changing pressure, there's not a changing volume or a changing temperature. So we use PV equals nRT. Now if there was a change in pressure, temperature, or volume, then we would use the combined gas law, which is this. But because there is no change, instead it gives us 3 of the 4, we use PV equals nRT. Now the first S is substitute, very easy. You just take your pressure, volume, and temperature and plug them into that. So we have 1.5 times the volume, which is 2.0, is equal to the moles, which we are looking for the moles, that's the unknown. Then we multiply it by R, and again, R is a constant, is always going to be this value right here, 0.0821. Real quick, just a little side note, make sure that it's 0.0821. A very big mistake is some students, and it's very common, do 0.821. This is not correct. You need to make sure that you add that 0 in there. So make sure you are adding that 0. And then the temperature is 321. All right, and then all we do is solve for moles. Moles is going to be equal to the 1.5 times 2.0 divided by 0.0821 times 321. And then you type that in your calculator, and you end up getting 0.11 moles, and it doesn't even say moles, it just says of gas, so it's moles of gas. And that could be any gas, whether it's hydrogen gas or helium gas or whatever. So 0.11 moles of gas, and that's our answer. Smiley face, because we're happy. Let's do the next problem here. This one gives us pressure. Okay, so the given in this situation is 6.5. It gives us moles, and it gives us volume. And I just cleaned it up there a little bit. Now what it's asking for is, what is the temperature? So the unknown is the temperature. That's what we don't know. Now again, we're given 3 of the 4 variables, and it's asking for the 4th. Again, there's no change happening. If there was a change, we would use this, but there is no change happening, so we use this, which is PV equals nRT. And then first S is substitute, so that's easy. So we have 6.5 times 9.3 equals N, which is 2.3, times R, which is a constant, which is 0.0. Make sure you add that 0, 821. And then we multiply it by T, which is our unknown. That's the thing that we're looking for. And then the last S is solve. T is equal to 6.5 times 9.3. And then we divide it by the 2.3 and the 0.0821, because those are multiplying temperature. So to move them to the other side, you have to divide them. And then we just type this into our calculator, and what you end up getting is 320.13 Kelvin. That is our answer. And we put a smiley face. This guy's so happy he's got his eyes closed. All right, so let's go ahead and move on to the next content. So just to review real quick, the ideal gas law. If you're given 3 of the 4 variables, you can calculate the 4th. R is a constant, and this first one is when there is a change happening. This is when there's no change, and that's how that works. So the last thing we're going to talk about today is Dalton's law of partial pressure, and this might be the easiest problem in all of chemistry. It is so easy. When you have a mixture of gases, right, and so for example the air around us is a mixture. We've got nitrogen and oxygen and carbon dioxide, and so there's some other things as well. But when you have a mixture of gases, the total pressure of that gas is going to be equal to the sum of all the partial pressures of the individual gases. So for example, let's say that there's 1 atmosphere of pressure around us right now. That pressure that is being exerted on us comes from the pressure of the nitrogen gas plus the oxygen gas plus the carbon dioxide, and then plus whatever other small amounts of gas there are. And each one of those gases exerts a certain pressure on us, and the sum of those pressures is going to be 1 atmosphere, because if the total pressure around us is 1 atmosphere, we're just saying that, that it is, then the sum of those would equal 1. And so it's really easy. So the partial pressure of gas is the pressure applied by individual gases. Each individual gas will exert its own pressure, and the sum of those individual pressures is the total pressure. And so notice how we have P total is equal to P1 plus P2 plus P3, and then we've got the dot dot dot. The reason why there's the dot 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 is it depends on how many gases there are. So if you have a mixture of 2 gases, you're going to have 2 partial pressures. If you have a mixture of 4 gases, you're going to have 4 partial pressures. If you have a mixture of 10 gases, you'll have 10 partial pressures. And so one hint when you're reading a problem is if it uses the word partial pressure at all, it's going to be Dalton's law of partial pressure. All right, so let's go ahead and take a look here. So a container holds a mixture of helium, neon, argon, and xenon. The partial pressure, oh, there we go. We know it's a partial pressure problem, so we know the equation is going to be the total pressures equal to sum of partial pressures. The partial pressure of helium is 1.1. Okay, so the partial pressure of helium is equal to 1.1. The partial pressure of neon is equal to 0.87. The partial pressure of argon is equal to 1.5. And the partial pressure of xenon is equal to 0.6. These are all atmospheres. And the question is, what is the total pressure? Okay, the total pressure is what we're looking for. Well, again, the total pressure is equal to the partial pressure of the helium plus the partial pressure of the neon plus the partial pressure of the argon plus the partial pressure of the xenon. You just add them together and you get the total. And so substitute partial pressure of the total is equal to 1.1 plus 0.87 plus 1.5 plus 0.6. Then you just add it together and you get a total pressure of 4.07 atmospheres. And that's your answer. And smiley face, because we're happy to get the correct answer there. All right, so these problems are really easy. Let's go ahead and do one more. This one's a little bit different though, because look what this one does is it gives us a total pressure. So the total pressure is 455. And it says that there's 3 mixtures, or there's 3 gases in the mixture. There's oxygen, hydrogen, and methane. And it says the partial pressure of the oxygen is equal to 311. It says the partial pressure of the methane is equal to 27. And what it's asking for is the partial pressure of the hydrogen gas. So that's what it's asking for. So this one is a little bit different because the equation is going to be the total pressure is equal to the partial pressure of the oxygen gas plus the partial pressure of the methane plus the partial pressure of the hydrogen gas. And when you substitute it, you see that it does give us the total pressure, which is 455. It does give us the partial pressure of the oxygen, which is 311. It does give us the partial pressure of the methane, which is 27, and it's asking for the partial pressure of the hydrogen gas. So how do we solve for the partial pressure of the hydrogen gas? It's very easy. You just subtract. You take your 455 and you subtract this and you subtract this to get your partial pressure of hydrogen gas. And you just type that in your calculator and you get a partial pressure of hydrogen gas to be 117. And that is going to be kilopascals because all of these are kilopascals. And there it is. And it's that simple. So that's all we have. We learned about the ideal gas law. If you have 3 or 4 variables, that's going to allow you to calculate the fourth one using PV equals nRT. Then we learned about Dalton's law of partial pressures, which states that all of the partial pressures added together will give you the total pressure. And that's it. So come to class with questions. Have a great day and take care.